for example, we have a reaction there, the N2O5 going to NO2 and O2. We look at that to write the equilibrium expression, not the constant, or not the value of the constant, because we don't know what the number is going to be. We write by starting with K. K describes, remember, we're talking about equilibrium. And then the general format is going to be products over reactants. That being said, the products of this are NO2 and O2. The other thing we do from the law of mass action, whatever the coefficients are for the balanced chemical equation become coefficients in the equilibrium expression. For example, there's a 4 here. The O2 has no coefficient, so we let that one go. Products over the reactants. Reactants in this case, N2O5 raised to now the second power. That is the equilibrium expression for that reaction. We don't know what the equilibrium constant K is. We don't know what the numerical value is. But this shows us where it's going to come from. In the brackets, these species that are in the brackets, the reason they're in brackets, the brackets indicate concentration. That is the concentration of each one of those viewed with the different powers in play. Because we have concentrations being used on the top, concentrations being used on the bottom, the equilibrium constant K is a unitless quantity. We could also get a sense, because of the way it's written, it's products over reactants, where the reaction lies. That is it equally split, that you have an equal amount of products and reactants, or is it higher on one side or the other? For example, if K is much less than 1, K being much less than 1 means that the number on the bottom has to be the larger number. If that's the case, that it's the larger number, that says that reaction is essentially all sitting at the reactant. Not much has gotten off to make product. The term that they'll use for this one is reactant favored. So we got a very small value for K. It means all of it sitting as reactant. Very little made product. Some did. For the most part, most of it is staying in the original form. Conversely, the opposite, if K is much greater than 1, that means the numbers at the top, the products are very large and the reactants are very small. This is product favored. And finally, if K is exactly 1, we can look at it as it's equal on both sides. There's an equal amount of product and reactant. So we have 3 different conditions. And we'll start to see K values, we'll start to calculate K values a little bit. But keeping this in mind, it tells you where the product will lie. Whether or not you're making a whole bunch, or whether or not it's setting at its equilibrium where more of the reactant or more of the product is present. One thing we can do with the equilibrium constants, they're written, for example, this is written for the reaction going in the forward direction. That's our general trend. This is written when you write an equilibrium expression for reactant going to product. A couple rules for these constants. If you have a reaction such as this, here's our reaction, and you know what the K value is, K for the, we'll call it the forward reaction. If you want to know what that equilibrium constant is not for the forward, but for the reverse reaction. That is, if they would give you and ask you what's the equilibrium constant for that, because we are simply changing the direction of the equilibrium constant to find this reaction, this K would be 1 over the initial one. So if you have a reaction and you flip it around, you want to know the other equilibrium constant, just take 1 over the original equilibrium constant. That's a rule. We'll see a problem with that in just a second. A lot of times they'll give you a reaction with its equilibrium constant and ask you what's it for the reverse reaction. 1 over the number will give you that value. The other one that they can ask you is they can give you a reaction just a generic ABC reaction, and then ask you, what is it if I scale the reaction up? That is, I take everything there and I multiply it by a number. Let's say, here's our equilibrium value K. I want to know if it's where N is some number, some whole number. That is, I multiply every coefficient by a number N. The rule for that is that if we do that, the new equilibrium constant is the original equilibrium constant raised to whatever that number is. You multiply the whole thing by 3, then you take the equilibrium constant and you raise it to the 3rd power. That's the relationship that we can have for that. Your book goes through and shows you a bunch of the derivation. Be comfortable with the way that we do it, but I'm not worried about the derivation between the different methods. The other thing we can do with an equilibrium constant is we can add reactions together. For example, so we have 2 reactions. Each one of them has an equilibrium constant. The question is, what's the equilibrium constant for the overall reaction if I add the 2 reactions together? If I add these 2 together, and then A goes to 3C, because both the 2 B's cancel out. Well, if I add 2 reactions together and they have their own equilibrium constants, then the new one, K3, is K1 times K2. So equilibrium constants tell us where the equilibrium lies, what value it has. Is there more product? Is there more reactant? And once we know them, we know them for one reaction, we can use them to find analogous reactions. We can take the parts and solve for other reactions. Let me show an example using the rules that we just laid out. Again, once you know one, you can use them in the other cases. You know the forward, you can find the reverse. You know one, you can find it if you multiply the whole thing by a constant. If you have 2 reactions, you're adding together, all you have to do is multiply together the equilibrium constants. So they're treated. The nice thing about equilibrium constants, you'll see quickly, is that unlike kinetic data, they're linked to the equations, and if you hold the conditions steady, they're tabulated. You'll see in the back when we start getting the other chapters, we have equilibrium constants that are known for types of reactions, not that it has to be kinetic data, but it has to be based just on the experiment that you're doing. Let's take a look at this. this reaction. You'll see that the equilibrium constant is a unitless quantity. And if we look at it, we see it's an extremely large number. There's a question about where does the equilibrium lie for this type, this number being that large. Certainly product favors. Most of this reaction turns into product. Now,
will we have to balance out the equation ourselves, or will they be provided for us?
it will vary by the problem. Most of them in this chapter, since they're worrying about the equilibrium topics, give you the balanced equation, so you can start from there. So if we know that one, the question is, what about this reaction? So if we look at that, this type of problem, first thing we do is try to notice what they did to the reaction. First thing we can certainly see, they reversed the reaction. They turned it around. Second thing they did, they've taken all the coefficients and multiplied them by 2. So based on the rules, if we're asked to find the new equilibrium expression, we have to apply the rule there. The rule says that if I flip a reaction, I have to do 1 over. Other rule says if I raise it to a coefficient, I have to raise it to that power that they multiplied it by. So for this one, the new k, a lot of times I'll go with k prime, indicating it's something new, is 1 over 2.2 times 10 to the 6th. That would be just for flipping it. That's taking the inverse because we're going the opposite direction. But then they also raised it to a power. Square this term. That applies both of the rules that we laid out. Putting that number in, get a number that looks like that. 2.07 times 10 to the minus 13. Based on that, would you say, does that reaction, as it's written here, work better than this one does? No, this was a dog. This is almost all of it staying like that. That number is so low that this reaction essentially does not work. It's going to stay all as reactant. Nothing is going over the product. This reaction was quite happy to go ripping forward. Now that you flipped it around, it's not going to work. That's the order of magnitude that we can get. So you'll see problems that say, here's a reaction, find a K for a new reaction. 3 rules to go by. We'll use and show the second one, that last rule, that multiplying reactions, in just a second. So find out what they did to the reaction, and then either multiply it by something or just reverse it.
I think I'm going to need you to look at my calculator, because when I keep trying to enter the equation, it's saying I have an error.
Okay, I'll take a look at that break, see what's going on.
Do any of these equations supersede each other? Like, do you have to do one before the other, or can they just be?
Right?
Does it matter?
No, you could have squared that and then taken the reciprocal of it, and it'll still work.
Even with step 3, like you already have to find K1 and K2 first, or will they give that to you?
They'll give you that. They'll give you K1 and
Okay,
K2.
that's
Yeah.
okay.
In fact, let's show you one with that.
Syntax.
Yeah, but then it's not.